All right, so we're going to run through the answers to our 5 questions that deal with law of acceleration. So let's take a look at number 1. A 1.5 kilogram box accelerates across a smooth tabletop at 16 meters per second squared, and then it's asking what unbalanced force was applied to this mass. So I always start these questions, especially as we start to get into forces, and even before when we were in the kinematics unit, make a givens list. See what you have, and then that will help you figure out what you need to solve for and how to get there. So it starts off and it gives us a mass. Okay, the mass is 1.5 kilograms. It's across a smooth tabletop at 16 meters per second squared. Meters per second squared is an acceleration. And so 16 meters per second squared. Notice that it doesn't give me a direction like east or north or anything like that, but it's accelerating across this tabletop. It's moving forward. Right? It says nothing in the problem about it moving backward or slowing down or anything like that. Now, what unbalanced force was applied? So this force is a net force. So this is what it's asking to solve for. What unbalanced force was applied to the mass? So the net force in the situation could be a variety of things. It could be somebody pushed it and there's a little bit of friction slowing it down, but the net force is the overall force that's causing this thing to move forward. So what unbalanced force, what extra force was applied to the mass to cause it to move? So mathematically, this is pretty straightforward. It's just taking mass times acceleration. So our net force is just equal to 1.5 kilograms multiplied by our 16 meters per second squared, and our net force works out to be 24 newtons. Notice I have kilogram meter per second squared here. And remember that 1 newton is equal to a kilogram meter per second squared. And so I have 24 newtons coming from that for an overall force. It needs a direction, so this thing is heading forward. Okay, so answer for the first one, really just multiplying mass times acceleration. Number 2, an object moves at a constant velocity and then has an unbalanced force of 20 newtons acting on it. So right away I see this object moving at a constant velocity. That means that it had no force beforehand. Its acceleration would have been 0. But then it has a force acting on it afterward of 20 newtons. And so the same thing again, this unbalanced force is a net force acting on this object. So the net force is equal to 20 newtons. Moving forward, acting on this object. And we know it has a mass of 37.5 kilograms. And so then it says, what is the acceleration while the force is acting upon it? So while these things are in contact and this object is being pushed, what is the acceleration that it moves at moving forward? So we have our equation, and if rearranging is something that's still a little bit tricky, then the triangle will work. We have force is equal to mass times acceleration, and so if I'm multiplying them, that vertical line means multiplication, horizontal line means division, and so force is equal to mass times acceleration, mass is equal to force over acceleration, or acceleration is equal to force divided by mass. So in this case, I'm asked to solve for acceleration. So acceleration is equal to my net force over top of my mass. Acceleration is equal to net force at 20 newtons. I don't need the forward part there, it's just going forward. 20 newtons over top of the 37.5 kilograms. So acceleration is equal to 0.53 repeating, and I take a look at my significant digits. There are 3 in each one, so I'm going to have 3 in my answer, 0.533 meters per second squared, and this thing is heading forward. So helps me just kind of visualize and see what's happening, reading through the problem, making my givens list, making sure I know what it is that I'm trying to solve for. Number 3, a race car undergoes a uniform acceleration of 8 meters per second. Okay, so this thing is traveling and then it accelerates at 8 meters per second. So acceleration, 8.00 meters per second squared, heading forward. If the unbalanced force, or the net force in this case, causes that acceleration, it says it's 6.0 times 10 to the 3 newtons. So the net force is going to be 6.0 times 10 to the 3 newtons heading forward. What would the mass of the race car be? So I take a look again at my rearranged formula. I've got F is equal to ma. So the mass of this would equal the net force, just a formula rearrangement, the net force over the acceleration. And so mass would equal, my net force is 6,000 newtons altogether, keeping in mind I have 2 significant digits out of that because of the scientific notation. So 6,000 newtons over top of 8.00 meters per second squared. The mass is then equal to 750 kilograms. And so take a look at significant digits. I had 2 coming from here, which makes sense then that my answer has 2 in it, because remember we always take the one with the fewest. So number 4, this is probably, if you were able to get through the first 3 relatively easily, this is probably where you started to read and maybe got a little stuck in terms of how to figure it out. So let's start off and make a givens list and then see where we have to go here. So a car having a mass of 710 kilograms starts from rest and goes 120 meters in 3 seconds. The car undergoes uniform acceleration during that time. So what unbalanced force is being applied to the car? So in the end, we're trying to find out what the net force is, okay, which is probably where you started. The mass for this thing was 710 kilograms, so if I knew the acceleration, I could just multiply these together and solve this question, but I don't know it yet. It doesn't give me the acceleration in here. What it does say is that it accelerates 120 meters during 3 seconds. So what can I do with that? Well, because there's acceleration and this thing is not constant speed, uniform acceleration should start to cue you back into the kinematics unit when it says something like starting from rest. So that means that we know that VI is 0, and we know this thing travels 120 meters, and it does that in 3 seconds. And so after that, if only I could find the acceleration, I could use that acceleration to help me find the net force. So at this point, you're probably thinking, so we're going back, and yes, we are. We are heading back into the Big Five, because anytime we have a question that involves acceleration or movement that is not constant velocity, it is a Big Five related problem. So if I take a look at my Big Five, I see, okay, which one am I missing out of this? This thing does not have VF in it, and so I have a formula that will help me solve this. I have my change in displacement, or change in distance traveled, is going to give me my initial speed times my time plus 1/2 times the average acceleration and my change in time squared. Now I can simplify this question pretty quickly because I have this VI is equal to 0, and so 0 times anything is 0, which means as soon as I plug VI for 0, that means this whole term cancels out, because it doesn't matter that time is 3 seconds, 0 times 3 still gives me 0. So really, delta D is equal to 1/2 AAV delta T squared. Now I need to rearrange this to solve for AAV. So remember, I'm going to go through essentially order of operations backward. I'm going to start with fractions. We're going to take whatever's in the denominator, multiply by it. So I'm going to multiply by 2. I've got 2 delta D is equal to AAV delta t squared. And then I need to solve for AAV, so I'm going to be dividing by t squared, divide by delta t squared, and then I can see that AAV is equal to 2 delta d over delta t squared. So once I have that, that means that now I can actually solve for my average acceleration, and then I can use that in my net force equation. So let's solve for average acceleration. Okay, AAV is equal to 2 times 120 meters over top of 3 seconds that are squared. Seconds, and that needs to be squared. So if I have 2 times, so let's get this next part going. I've got 2 times 120, that's 240 meters over 9.0 squared seconds, and 240 divided by 9 gives me 26.6 repeating, so AAV is equal to 26.6 repeating meters per second squared. I do need to keep in mind here that I've got 2 significant digits coming from this. But I'm not going to call that 27 because I don't want to mess up when I plug it into my other thing. I don't want to round anything too early. So really what I have now, let's go back up and see what we're looking at for the problem. Now I need to find the net force. So the net force is equal to my mass value, or mass times acceleration, which means that the net force is equal to the mass value at 710 kilograms, and my acceleration at 26.6 repeating meters per second squared. And so my net force gives me 240 divided by 9 multiplied by 710 gives me 18,933. So 18,933 newtons heading forward. Now I take a look at significant digits in this, and I notice that, remembering from before, I only had 2, so I've got 2 here, and it looks like the 710 only has 2, so that's 2 in the question, which means that this thing really is 19,000 newtons. So my net force at the end, and I'm just going to erase just a little bit there to fit this in. So my net force at the end is equal to 19,000 newtons heading forward. And so, like, I could also have called that 1.9 times 10 to the 4 newtons, and it would be the same thing. So hopefully, having seen number 4 now, number 5 might make a little bit more sense. And when we start to go through these, just keep in mind, anytime we deal with acceleration, the big 5 can be in play, because all of those big 5 problems involve uniform acceleration type problems. Anytime I have constant speed, that's when I can just say that the acceleration is 0, and the net force would be 0 as well. So let's go into number 5 here. An artillery shell has a mass of 55 kilograms. The shell is fired from the muzzle of a gun at 77 meters per second. The length of the barrel is 1.5 meters. And then, assuming the force and acceleration is constant while the shell is in the gun barrel, what is the force that acts on the shell while it's in the barrel? And it's really important here as you're reading this to understand that this whole thing is talking about while it is inside the barrel. So it does require me to read in between the lines a little bit here just to understand it. Let's start with our givens list. Shell has a mass of 55 kilograms. Okay, mass is 55 kilograms. The shell is fired from the muzzle of the gun at 77 meters per second. Now, this is the speed that it's going when it's fired from the gun, so outside of the gun. That's the velocity that it's traveling just as the bullet leaves the barrel. So that must mean that that's the final speed, because this whole problem is saying while it's inside the barrel, it wants to know the force. So 77.0 meters per second is the speed it would be traveling when it leaves the barrel. Now, that part also kind of leads me to look through the question and think, well, the bullet's not really moving until the gun is fired, which means that its initial speed is starting off at 0. Then I have a distance. I have the length of the barrel at 1.50 meters. And I'm in the same scenario because it wants what is the force, so it wants the net force, and in order to get the net force, I really need that acceleration to get there. So when I look at my big 5 in this case now, I don't have time in the mix, and so if I don't have time in here, that means that if I look at my big 5 sheet, I have this problem where I have Vf squared is equal to Vi squared plus 2 AAV delta D. And so Vi is 0, which makes this a little bit easier to go through, but I still need to rearrange this thing for acceleration. But all I really need to do is one step with this one, because this is all being multiplied together with the 2 times the acceleration times the displacement. So if I divide by 2 delta D on both sides, then what I notice after that is I have this relationship where I have average acceleration is just equal to Vf squared over 2 delta D. So AAV is equal to, I've got Vf squared, looks like it's 77.0 meters per second, over 2 times the displacement at 1.50 meters. Looks like I have an average acceleration that's going to work out to be 1,976.3 meters per second squared. So I'm just going to double check my math. 77 squared divided by divided by 3 gives me 1,976.3 repeating meters per second squared. Now, significant digit wise, I'm not going to round anything early, but it would be helpful to know where I'm at with this. I have 3 digits on each one, top and bottom, so I'm going to have 3 digits here that I'm going to kind of keep mind of when I start to look at it toward the end. So the last thing now, I have the net force. Net force is equal to mass times acceleration. The net force in this case, what I'm trying to solve for, is equal to the mass at 55 kilograms times the acceleration, which is what we just found, the 1,976.3 meters per second squared. And so the net force equals out, when I multiply this times the 55, to work out to be 108,698.3 repeating newtons moving forward. So using significant digits in this, the 55 only has 2, which means I'm going to have 2 in my answer. So the net force in this looks like it works out to be 1.1 times 10 to the 1, 2, 3, 4, 5 newtons moving forward. Could have also have said 110,000 newtons. Now, if you think about this problem in context, what it's saying is that if I have a rifle that has a barrel that's about 1.5 meters long, and we know its exit speed and how much the artillery shell has for a mass, that means that we need about 110,000 newtons worth of force to cause it to travel at that speed while it's exiting the barrel, which is an incredible amount of force over such a small distance and likely happening very fast. And given the variables that we have, we could actually calculate how much time that took as well to do, although we don't need to go there right now. So those are the 5 problems worked out for the acceleration area. So in the next video, we're going to go through and just kind of finish off the last little part There's just a couple parts to tie up before we move on to the next section into Newton's third law.